So in this learning module, we'll be introducing the concept of the center of gravity, the center of mass, along with the centroid. We'll also do a brief example problem, actually two, and then in the next learning module, I'll get you set up for the actual problem on the second part of your final exam. So we've been forced to use the center of gravity throughout this course, thinking back to the time that we first drew a free body diagram where we represented the weight of the body. And in that case, of course, we just represented the weight as a single force vector. And we had some intuition of what the magnitude of that force vector should be. Usually it's described. We're all familiar with the idea of weight. However, when we actually placed that force vector along the object, we were either always told where to place it, or we just assumed that we should place it at near the center of the object under some arguments of symmetry. So what are we really doing when we do that? Well, if we think about a body, we can kind of decompose it however we want into little pieces. And of course, all of those little pieces, they would have some mass to them. So they have weight as well. So really what weight is a force that is distributed across the entire body. But for modeling simplicity, we represent that distributed force, as we often do in this class, by an equivalent force couple system. Only in this scenario, we're choosing to place the force at a location such that the translational and rotational effects of all those little mini gravities acting on all the little portion of the object are represented by a single force vector applied at a particular point. So that's the key idea of what the center of gravity of an object is. It's the point at which you can apply a single vector of magnitude whose weight is equal to the total weight of the object and of location such that the rotational tendencies of all the little chunks of weight kind of counterbalance each other out. So we usually think of, if you think about practical life on a day-to-day basis, if you have an object with weight, you might ask yourself, is there a point that I can just push upwards and oppose gravity and completely balance that object? And if that point exists, if you think about it, what that must mean is that all of the kind of portion of the object that's on one side of where you're placing, it's tending to induce rotation, but that rotation is counterbalanced by all of the rotation that's induced by the stuff on the other side of the object. So just think of it as the balancing point. So how do we determine what that is? Well, here are the equations that we need to work with here on the left, and they look complicated, but they're really not. What the solid bar over x, y, and z represents here is the coordinates of the center of gravity. So these are the x, y, and z coordinates of the center of gravity. So if you think about what this is doing here, right, what would be, for example, x bar w? If we were to apply, so w, of course, corresponds to the total weight of the object. So we're talking about once the body has been modeled under this equivalent force system. So if I look down here and I take x bar, sorry, I'll get my mouse here, times w, what is that representing? That's representing the tendency of this one single force corresponding to the weight to induce rotation about the y-axis, right? It's just a moment about the y-axis. So what this is saying is that whatever, when I model all of the weight of the individual chunks of the object by a single weight force, that single weight force's tendency to induce rotation about the y-axis better be the same as, remember, an integral is just an infinitesimal sum. So the sum of all of these, what is dw here? That's the weight of all these little individual blocks. So x tilde dw is just the tendency of this little chunk to induce rotation about the y-axis. So if I sum that up for all the little chunks, I just need to make sure that these two things are equivalent in order for these to be an equivalent force system. And that same idea just applies for all the other axes. For example, y bar w is describing the tendency of the single equivalent force system to induce rotation about the x-axis. This is just saying that for your single force representation of the weight, the tendency to induce rotation about the x-axis has to be the same as the sum of all of the tendencies of the little chunks to induce rotation about the x-axis. And I won't bore you for the remaining equation, but you get the point. So if you think about it, since in our scenarios for the gravitational models that we're using, we're modeling the acceleration due to gravity as constant, mass and weight are just proportional to one another. So in our models, whatever the center of gravity is, another way that you could call that is just the center of mass. And you could go back to all these equations, and rather than working with weight, which is just going to be g times m, you could just swap all your w's with m's, and you could define that as the center of mass. A similar idea is the idea of a centroid. Now, technically, the centroid is a kind of geometrical property that applies for the majority of cases we're going to look at as an area, but it doesn't have to be an area. If you look at some of the examples in your book, you can define it for a linear trajectory as well. But basically, for a given surface, it's a property that defines the geometrical center of that surface. So even though it's not kind of tied to mechanics or tied to the ideas of weight, it's easier to understand it if you think about it in terms of weight. So any surface, when you're looking at it, just think about if that represented a uniform density surface. If it represents a uniform density surface, then the centroid is the center of mass. And we know this. Imagine you had a rectangular plate in front of you and it had uniform weight. Where would you balance it? You'd balance it by putting your finger right in the middle. Imagine it was a triangular plate. Where would you balance it? You'd balance it by placing your finger more towards the right side, in this case, since the majority of the area is towards the right side, and more towards the bottom, since the majority of the area is towards the bottom. You might not know exactly where it's at parametrically as a function of the geometry, but intuitively you know kind of where it's at. In addition, you kind of notice both for this example of the rectangle and this example of the cylinder, there's a lot of relationship between symmetry of the area or the volume and the centroid of the particular object. Namely, if you have lines of symmetry, you know that the centroid will be located along that line of symmetry. So not surprising that, like going down here for the semicircular arc, clearly we have a vertical line of symmetry, and that's where the centroid is at. It's on that vertical line of symmetry. In the case of the quarter circle, the line of symmetry would be at a 45-degree angle. That's where the centroid is at. Notice that we're just saying it's along that line. How far out it is along that line is something you would have to compute. But we know in the case of the semicircle, it's going to be farther out than just halfway because the majority of the area is farther away from the origin in that case. The one thing I wanted to bring up to you is that the centroid of a shape need not necessarily be on the shape itself. So think about drawing like a washer or a donut. So a circle with the middle cut out. There you have two lines of symmetry, right? You'd have a vertical line of symmetry and a horizontal line of symmetry. So since you know the centroid has to be on both axes, it must be right there at the middle where they intersect. So in that case, technically, that middle is cut out. So the centroid is not on the actual area itself. And that's okay. And all that means is that you couldn't balance that area if you viewed it as an area with uniform weight by a single upward force. Let's look at some examples of how you compute centroids for problems in this chapter of the text. So really what this boils down to is kind of just making sure that you remember your single variable integration. So say you had an area, because if they're simple geometries, you can either look them up from a table or enforce symmetry. But say you have an area that's bounded by kind of straight lines on two sides. Here along the horizontal dimension, it's bounded by a straight line from 0 to 1, and along the vertical dimension, it's bounded by a straight line from 0 to 1 as well. But along this other edge, it's bounded by a cubic relationship, where I know that the height at any point in x is just the x value cubed. So if I'm out here at 0.3, what would the height be? It would just be 0.3 cubed. The question is, can I use these formulas? Now remember, when we're computing centroids, we would swap the w's with a's, since we're talking about areas in this case. So can we use these formulas in order to locate, since we're only in two dimensions, x bar and y bar? So we basically want to solve for x bar such that x bar a equals the sum of all the little chunks that will divide the area into x tilde dA. So probably didn't make much sense to show you that formula, but I will show you here. So really what this boils down to in the problems in the book is, since we're only considering kind of one-dimensional or single integrals, not double integrals, what is going to be the easiest variable to integrate with respect to? So if I had this kind of cutout parabolic area, if I were to divide it into little rectangles, and I would consider the variation in those rectangles all the way from x equals 0 to 1, the question is, for that little rectangle, can I compute the three pieces of information that I need? I need the centroids, the x and y coordinate, along with an expression for the area. So if I take an infinitesimally thin rectangle, what will its area be? Well, the area of any rectangle is just the width times the height. In this case, we're going to allow the width to be our dx. We're going to allow it to go infinitesimally thin towards 0. And the height will just depend upon where we're at in x. So at any value of x, the height will just be y, and the width will be dx. But remember, I'm going to integrate. I'm going to allow x to vary from 0 to 1. So I'm going to want anything that involves y to be expressed in terms of x. So rather than write dA as y dx, I'm going to write it as x cubed times dx. Now, notice that that's only a valid assumption when the width of this rectangle becomes infinitesimally thin. When it has finite width, like they're showing there, it doesn't hit the curve perfectly at 2 points. It's kind of underestimating the area in this case. But the calculus argument of the Riemann sum is that as this becomes infinitely thin, that will be an adequate representation. So I find the infinitesimal area, y dx. I choose to represent y as a function of x since I know I'll be integrating with respect to x. This rectangle for any x value, where is its centroid? Well, that's what we're denoting as the x tilde and the y tilde. Those are just the centroids of the little infinitesimal area. Well, since this is infinitesimally thin, I can just say that its centroid is just whatever value of x I'm at. So that's all that this is saying. When the rectangle is located at coordinate x, the centroid is just whatever that coordinate is. And again, you might say, well, why isn't it x over 2? Well, remember, x is how far away you are from the origin. So if you made it x over 2, you'd be saying the centroid is over here. The idea is that's an infinitesimally thin rectangle, so the point is the middle. However, for the height, right, the centroid is just going to be half of that height. So if the total height is y, then the centroid would be y over 2. Again, we'll choose to express y as a function of x in order to support our integration. That's why we're saying y tilde is just y over 2, or since any point y is x cubed divided by 2. Now it's just a matter of doing the math. If you think about it here, these are those same formulas that you had back a couple slides ago, only the w's are a's, and we've solved for the two quantities of interest, x bar and y bar. So if you were to multiply this back out on both sides, what this would say is that basically this technically is the first moment of this area, but we're not going I want to stick with the theme of statics and use the idea of weight. So if this were to be infinitesimally thin, this would be a quantity that's proportional to the centroid times the total weight. So this is kind of like this diagonal product is related to the aggregate model. Think of integral dA as just being the total weight under the case that something is uniformly distributed. So what this represents, x bar times w, is the total tendency of this object to rotate about the y axis. And what I need to ensure is that it's equal to the sum of all the tendency of those little rectangles to rotate about the y-axis. So really, it's just a matter of plug and chug here. We have an expression for x bar, that's just the centroid of each little rectangle, that's just x. We have an expression for dA from the prior slide, it's x cubed dx. dA again in the denominator is x cubed dx. We're going to sum all the rectangles by allowing x to vary from 0 to 1. And this just becomes a case of taking the antiderivative of a power function. Remember, when you take the antiderivative of a power function like x to the fourth, you add 1 to the power, it becomes 5, and you divide by that new power. And you can always check that your antiderivative is correct by asking yourself, if you go back and take the derivative, do you get back to the original function x to the fourth? And yes, the derivative of 1/5 x to the fifth is x to the fourth. Remember, since this is a definite integral, I need to evaluate that antiderivative from the upper bound to the lower bound, and just do the math, and you will find 0.8 meters. And you look at this and you tell yourself, yeah, the centroid should be more towards 1, not towards 0, since the majority of the area in x is over here. So 0.8 meters. By a similar fashion, when we compute the y value, we'll know it should be more towards 0 and not towards 1. And that's exactly what we see here. So if you notice, just all of these expressions are simple integrals resulting from plugging those expressions for the centroid and infinitesimal area of the rectangular strips in.